start now. Welcome to our Friday Physics Colloquium. For those who didn't sign the attendance sheet for 155, 180, and 280, please do so. Don't forget to do it. It's my pleasure to introduce you to Dr. Katherine Elder. She's our alumni. She graduated in 2019. I'm just going to read a few things about her bio. She's working at the Radio Astronomy Instrumentation with her telescope. She was an intern as an undergraduate at the NASA Goddard Space Flight Center in Infrared Detector Lab. She started her PhD in 2019.
Well, I started 2020.
And she graduated this past summer. Her focus is on identifying and modeling systematics in radio telescopes, specifically in the long wavelengths array, the Murchison wide field array. And after her recent graduation this summer, she began working at the National Radio Astronomy Observatory, where she's currently a postdoc and is testing on next generation very large array. And her talk is going to be about this. So welcome, Katherine.
So as he said, I will be talking about my work on commissioning and testing the next generation very large array. But I remember being an undergraduate here, and that most of you probably don't have a lot of experience with radio astronomy in general. So my talk outline, I'm going to start with just giving background on what NRAO is, the VLA and VLBA, and the many acronyms that you're going to be hearing. I will be defining. And then I'll actually get into the next generation very large array and what the design and science goals are. The testing, which is where my job actually comes in, and then I'll end with the current status and future work with this. But to start off, just what is radio astronomy? So you should be familiar with the electromagnetic spectrum, and for astronomers, the issue with actually observing all of these different frequencies and wavelengths is that the Earth's atmosphere interacts with and affects what you can see. So from the ground, we can actually see the optical wavelengths, so that's here. So there are some ground observatories. But then when you get to shorter wavelengths, we have to go up into space. So you hear about things like the James Webb Space Telescope and Chandra X-ray Observatory. You have to get into space to actually see those frequencies. But if you go to long wavelengths and shorter frequencies, lower frequency, there is actually a period, a window that we can see these radio frequencies from the ground, which is great because it means it's a lot cheaper to build your telescopes. Because if you're not having to go to space, you can actually build large telescopes here on the ground. But some more history of it, radio astronomy was actually discovered in 1933 by Carl Jansky. He was looking up at the sky and heard a radio signal from the Milky Way. So that's actually something that you can still do. You can talk to me afterwards if you're interested in building your own radio telescope and listening to the Milky Way, even from the middle of a city. If you can hear it in Phoenix, you can hear it in Fresno. But then the first radio telescope was built in 1937. And what radio astronomy is defined as is being the roughly 3 kilohertz to 900 gigahertz range in frequency. So that covers things like FM and AM radio and TV broadcasting. And the wavelength is 100 kilometers to less than 1 millimeter. So it's a very wide range of frequencies and wavelengths. So that affects the different types of telescopes you use, but that's all what radio astronomy is. But what do you actually see with radio astronomy and radio telescopes? So this is an image of M50, the Manatee Nebula. So this is in optical. This is in radio. So with radio, you can actually see the gas and dust and emission that is invisible to optical wavelengths. And then you can also see things like supernova remnants. So again, you have optical image versus you can actually see the shock wave of a supernova having exploded. So you can find out the physics and understanding of what happens with supernovas. And then possibly more well known is the image of the black hole that the Event Horizon Telescope imaged many years ago now with M87 star. So you can actually see images of black holes, which is a very big deal because the whole point of a black hole is that it absorbs all light. So clearly you can't see it with an optical telescope, but we can actually see it in the radio. So radio is something that is incredibly useful. These wavelengths can show a lot of what is considered invisible to the unaided eye. It can see through dust in the universe that would block optical telescopes. It can actually see through that to light that is further away. So then, how do radio telescopes work? So this is an example of a radio telescope, very similar to some that I'm going to be talking about. So you have your radio source, so it could be a supernova, it could be a galaxy, it could be something else that's emitting light. And then it comes down, and very similar to optical telescopes, in this case you have a reflector that will reflect all of that light and put it towards into your feed that will actually read and record that information and send all of that data to a control room for processing. So in this case, some radio telescopes are just essentially a receiver. So you have just, they can be very triangular or just very small on the ground. But a lot of them that you'll see, and this is like if you have dish TV, you'll see antennas like this that are actually reflecting into this secondary reflector to actually record the data. And one of the major characteristics, and something that I'll talk about, is angular resolution. So it's defined as wavelength divided by diameter. So when your wavelength is in millimeters, your diameter of your telescope is in kilometers. That's very difficult to achieve. The largest radio telescope single dish was Arecibo, and Arecibo was so large that it actually collapsed many years ago now. But it's just very, very difficult to get incredibly large telescopes. So in that case, especially with radio astronomy, it's really easy for us to do something called interferometry, which this XKCD comic talks about, where it's you can combine multiple elements to act as one. Now, we can't actually do it with dogs. You can't take two dogs and make one big dog. Little dogs already think they are big dogs. But we can use that concept with radio, and the way it works is you get multiple dishes, you get multiple antennas that are all observing the same thing. You do lots of electronics and math, you multiply those signals together, you get what's called visibilities. Then you do a Fourier transform, and you get a pretty picture of the sky. And I will note, as a former physics major, Fourier transforms are some of the only math that I did in grad school as a radio astronomer. So then when I got to the end of my PhD and my advisor told me we need to do the math to figure out how this works, I told him I don't do math anymore. All I do is Python coding and Fourier transforms. But I did actually remember how to do physics, which is good considering I'm talking to you all in your physics department. So, but the radio telescopes actually are already doing a Fourier transform as an interferometer. But the point is that we can take a bunch of telescopes and make images So instead of trying to make a single telescope be as large as possible, you can make a bunch of individual antennas and spread them out to get that diameter that you need. So I work for the National Radio Astronomy Observatory. This is one of the, I'll be biased, premier radio astronomy observatories in the world. The headquarters is located in Virginia, as well as the Green Bank Observatory. And then New Mexico has the very large array and the operations for that. And the primary telescopes that they run are the 100-meter Green Bank telescope. So that is actually a single dish that is 100 meters across. It's very, very large. And then the VLA and VLBA I'll be talking about. ALMA is in Chile. I will not be talking about it because I do not work with it and know very little about it. But the others I do work with, so I know a lot about them. So I'll talk about them. But NRAO, this is actually an image of the GBT, the Green Bank telescope, so you can see it is incredibly large, and there's your secondary reflector, and there's your dish, and it's very, very large. But NRAO as a whole was established in 1956, and the Green Bank Observatory was opened in 1957, and they immediately started building radio telescopes. So they started with a 12-foot antenna and then moved up to 85 feet and 140 feet and then 300 feet. The first interferometer was built in 1964, and then Congress approved the very large array in 1972. And actually the GBT was first came online in 2000. So the 4 telescopes that I listed previously are the only ones still in operation. All of the other telescopes that NRAO has built have been decommissioned since then because they've been around for a very long time and things get old and you improve technology and move to other telescopes. But even the NRAO expanded to include a telescope on Kitt Peak in Arizona in 1967. So they have a long history of radio telescopes and expanding to other locations as well to get other people involved, and started collaborating internationally with other radio telescopes in 1968. So focusing on the very large array, it's been observing since 1976. This is a photo of antenna 1 from 1975 when it was being moved into position. So this is your antenna. These are the people down here at the bottom. This is the vehicle that moves the 230-ton antennas, because these move. You can move them down a railroad track. And this vehicle can lift these antennas and drive them up to 5 miles an hour, which I know doesn't sound like much, but when you have a 26-meter tall antenna that weighs 230 tons, that is insanely fast. They've never dropped one. But it's been observing since 1976, so it has a very long history. There are 28 antennas, but only 27 will be operating at a time, and the 28th will be in the barn for maintenance, so each antenna regularly goes through maintenance. But these are 25-meter diameter dishes. They observe from 1 to 50 gigahertz, so in wavelength that's 30 centimeters to 6 millimeters. And they have 0.2 to 0.04 arc-second resolution. So that's, again, it's very, very small portions of the sky is able to actually be resolved depending on how the array is configured, and I'll show you some maps of it. But the VLA is probably the most well-known radio telescope, I would say, due to the fact that it was featured in the movie Contact, which I'm discovering fewer and fewer people know. So I actually don't know if any of the undergrads in the room have ever seen Contact, and that does make me very sad inside, but Contact is a very well-known movie that takes place at the VLA. And then more recently, the very beginning of Pluribus was filmed at the VLA. Pluribus, I haven't seen. I've heard a lot about it. It was filmed where I work, so before I worked there. But interestingly, both of these instances of it being in media are involved with the search for extraterrestrial life, which is something that we don't do at the VLA. We're not part of searching for aliens. So it's funny that that's what it's been used for in media. We leave that for other astronomers. But as I said, there's multiple configurations. So you can see in these images, the antennae are very close together. So there are 4 configurations. As I said, the antennas can move. So in what's known as D configuration, everything's very close together. So you can see these, it's hard to see on the projector, but there's images of little antennas here. They're all spread out in this Y shape. And the longest baseline that you can get, so the longest diameter, widest diameter that you can get for this telescope is about 0.6 miles. And you can see this is the barn here where antennas go under construction. This is the visitor center, so you can go visit. So, but notice, you know, you can pay attention, and as I said, these antennas move. So if you look closely, you can't see the visitor center anymore because at A configuration, it stretches to 22 miles across. So this, in D configuration, is right here in the middle of this image. You can actually see these little white dots here are the only antennas that are present nearby in A configuration. And this is what it looks like spread across to the valley in New Mexico when it's in A configuration. So this is why you have that difference in angular resolution, because it'll change depending on how your antennas are spread out, and therefore what is that diameter of your telescope. So we can have very short baselines that can be useful for a more broad emission, and then longer baselines are used for more densely packed things. And I'll show some examples of that. So, but yes?
Do they need to be in the same altitude?
We account for the fact that there's going to be differences in elevation, but actually it is fairly level where they are. So they are at a fairly similar elevation, but that is something that has to be accounted for when you're looking at their positions. So what science do we do with the VLA? So we can look at radio galaxies. So these are some examples of some radio images where you can see this is an example of improvements in the telescope. So this was old sky surveys, what had been able to see, and then the instruments were upgraded, and this was the new images. So you can actually see something now in the bottom, but able to actually see emission from radio galaxies and learn about the shape and size and what's happening there. You can see quasars. So this is an image that was taken in 1996 of a quasar with the VLA, and so you can see the jets of emission coming out of your actual quasar. You can see supernova remnants, which I already had talked about. This is the image of it, sorry. So in different polarizations as well. And then you can also see fast radio bursts, so that's quick things that'll happen. I don't have image examples, but these are all different things that you can see with the VLA, and there's lots more that we can do with it. But the point is that there's a lot of astronomy, a lot of space that you can actually see with radio telescopes, and getting these large telescopes, large diameter, large baseline to be able to observe these. But the VLA is limited. We get up to 22 miles, but that's still not large in comparison to some of the wavelengths that you would like to see and the resolution that you would like to see. So since 1993, NRAO has also been running the very long baseline array. So we had the VLA, now we have the VLBA. Again, with the acronyms. But this is a collection of 10 individual antennas that are scattered around various places in the US. The longest baseline is between Hawaii and the Virgin Islands, but it is scattered and is able to work with other telescopes, so can work in connection with the VLA, but is specifically designed to be a very long baseline, very large diameter to be able to observe at a higher resolution. So, as I said, there's 10 antennas, each of them it's still based on the VLA antennas, so it's 25 meters, but this observes from 0.3 to 96 gigahertz, so it goes higher in frequency than the VLA, but the 0.17 to 22 milli-arc second resolution, so it can see incredibly small things in the sky. Can resolve very detailed. And the maximum baseline is 5,350 miles. So it's essentially an incredibly large telescope. So this was an improvement for the telescope of being able to be even bigger, have even higher resolution than the VLA. So it does do very similar science as the VLA. So again, we can observe radio galaxies. So this is an example of what is visible with the VLA. This is what was in the visible spectrum. And then this is with the VLBA. So it zoomed in on the little thing that's causing the jets. And we can actually see the emission and see what is coming from this radio galaxy. Where are the jets? What's actually emitting it? So instead of, if you're looking at an object and you just see a large blob, you don't know where the center of it is of the object that is actually emitting this jet or these lights that you're seeing. And with the VLBA, we can actually zoom in and see the center of a galaxy. You can also see black holes. So this is an example. So the blue is from Chandra, so this is from X-ray, what was able to be observed. And there's just these dark spots, black spots, where they're black holes. They're absorbing all of the light, so you can't actually see anything. But you can actually zoom in and radio with the VLBA and see the black hole actually emitting light and see it moving. And that gives a lot of information about black holes and how they work that you wouldn't be able to get otherwise. So this is another image where you can see a black hole and jets coming off of it. And the jets are all moving in the same direction. It's not uniform. So that can tell us information about black holes' movement and how they're evolving and what's causing these things. There's also been recent searching for dark matter. So this was an observation with VLBA of noticing, you can see this sort of, it's curved in, something is squeezing the light being emitted that we can't see. But there's something there. So you can search for dark matter with this. And even, I think that this is really interesting, you can actually find out information about asteroids. So this is a lot closer, not something so far away and foreign as a black hole, but actually asteroids that are coming in by using the diffraction pattern that you get by being an interferometer. You can actually learn information about asteroids coming through our solar system and where are they coming from and what are they made of.
Excuse me.
Yeah.
Could you go back one slide? So what is that? What is it?
So this is light from two compact objects, and you can see the objects and then jets being emitted out of them. And then there's no other object, but something is squeezing what we're seeing emitted from it. So that would be I don't do research into dark energy, dark matter. I don't really know, but this is something of indicating maybe we can use radio telescopes to try and find dark matter. If you're seeing something's interacting with the light that we can't see.
So it's squeezing the light?
Mhm.
Okay.
As if there was something very large there that would be interacting with it, but there's nothing present that we
Thank you.
observe. So with all of that, I hope you've gotten an idea of there's a lot of science that we can do with VLA, VLBA, lots of things that we can learn about astronomy, but like with needing to upgrade to the Very Long Baseline Array, there's always new development of technology, new needs coming up in science, and a desire for the next thing. So you have the next generation Very Large Array, because sometimes astronomers are not creative at coming up with names. We said we're doing the next generation of the Very Large Array, we're going to call it the next generation Very Large Array. So I work on the ngVLA. So the ngVLA is going to be observing from 1.2 to 116 gigahertz. So this is much higher frequency than we've had access to, which means much smaller wavelength. Now, as a note, my research previous to this has been in radio and has been in low frequency. So I worked in 80 to 300 megahertz, where the wavelengths are on the scale of meters. There were arguments about trying to get the ngVLA down to 1.2 gigahertz because those feeds need to be very large because the wavelengths are getting longer, and the engineers were saying, hey, this is very large, it's going to add weight to it. Is it really necessary? No one uses low frequency. Hearing 1.2 gigahertz referred to as low frequency when most of my research was around 100 megahertz was a big transition for me, moving from PhD to job at NRAO. So it's very amusing to me whenever people talk about things being low frequency at NRAO. It's like, you're still in gigahertz, you're high frequency, you're wrong, it's fine. But this is the frequency range, and the goal is that it's going to be 10 times as sensitive as the VLA. So this is an example of the sensitivity versus frequency, and the ngVLA is basically going to be here's red, so you can just think of y-axis is how sensitive is it. Red down here is the VLA, and this peach color is the ngVLA. So it's not only going to be at a much higher frequency, so we'll be able to see things that the VLA can't see, but also just it's going to be 10 times as sensitive, able to see even more objects in our universe, able to resolve them and see them. Of course, there's always going to be sections of the frequency range that we can't see, and there's lots of other things in our way, but it's going to be 10 times as sensitive and going to have 10 times the resolution. So I kept talking about angular resolution. So again, here's the VLA in angular resolution, and down is good. Most of the time up is good, down is good. And the ngVLA is going to be all the way down here. And there's lots of other radio telescopes and other frequency telescopes here that all of their angular resolution tops out here, and the ngVLA is going to be much more sensitive, be able to resolve even smaller objects. So the goal is to improve on and eventually will actually replace the VLA and VLBA. So another improvement, something that I find very interesting, this is an example of the VLA versus ngVLA slew speed. So slew is how quickly does it move. So this is the VLA, if I can get it to work for me. So here's a video of the VLA moving in azimuth. So it's rotating. It's not moving up and down, but it's rotating. And you can see it's rotating very slowly. Again, this is a 230-ton object, so it's moving very fast. But it's moving very slowly. And then this is the ngVLA. This is real time. This is our prototype antenna. VLA is still going, still slowly going. So it's a lot faster. And I actually did a project with a scientist at NRAO, Rick Curley, where we were observing the moon. And something that happens when you're doing observations is you have your source that you're trying to observe, and then you have to have calibrators. So these are very bright, known sources. You know all the information about them, so you can look at them, be sure you're still operating your telescope correctly, and then go back to your source so you can make sure that your observations are processed correctly. And you have to, in the middle of your observation, you're observing for 6 hours, and you're at your source for 10 minutes. And then you have to go to your calibrator and observe it for a couple of minutes, and then you can go back to your source. With the VLA, depending on where your calibrator is related to your source, it can take a very long time, actually, to move to your calibrator. So you have a 6-hour window that you're observing, and a big portion of that time is being eaten up by your calibrator. But hopefully you can find a calibrator very close to your source, but sometimes they're in a completely different part of the sky, and you actually have to rotate your entire antenna to get it. With the ngVLA, your observation time is not going to be eaten up as much by looking at those calibrators. It's zippy. It moves very fast. It's very fun to watch, but I also am an instrumentationalist, so these things make me happy. So that's another improvement that I'm very excited about, is just the speed of our antennas. So this is a map of the plan. As I said, we currently have a prototype that you just saw a video of. And then this is the plan for where the ngVLA antennas are going to be located. Instead of having 10 like the VLBA or 27 like the VLA, we are going to have 218. So also, our antennas are not going to be movable. They will be in a single position. We're not going to have to lift them up and move them to another location, because you don't need to. You have enough telescopes, you have enough antennas that they're all just going to be there available for you to use. So the core is still going to be located in New Mexico at the VLA site, and then it will expand out into several other states and into Mexico as well. And then we will have long baseline antennas as well. So instead of a single antenna at a location, we'll have 3. And in some cases, we will be taking over from the site that currently hosts a VLBA antenna, and in other cases, we're going to be moving somewhere else. But we're still going to have these long baseline locations. So not only do we have this core, but then we'll have similar baseline length that we have with the VLBA. Yes?
I'm curious if the configuration, if there's a physics reason why it looks like a spiraling starfish. Or is that just artistic?
Great question. It has something to do with the resolution and varying baseline lengths. And I don't know the reason behind it. This has been set for many years, and I don't remember reading what the reasoning behind it is. The core is mostly just packed together, randomly situated, and then, yeah, it goes into that spiral. So we're going to have a lot of antennas. So science with ngVLA, of course, what are we going to be doing that is improving on what we're currently doing with the VLA and the VLBA? So some of the main science goals for this include looking at solar system formation. So actually being able to look at neighboring solar systems and learn about how they form. So this is an example of this top image was an observation with ALMA. And then this is an image, a model simulated image of what we expect to be able to see with the ngVLA. So this is, you can actually see the planets in this solar system. So we can learn about different planets and actually be able to observe more masses of exoplanets as well than what we've been able to see. But we can find out information about how solar systems form. We can also use it for astrochemistry. So this is the less exciting type of plots that I look at, which is just lines. But you can actually see the individual molecules that make up different objects that we're seeing, and so can use this for initial conditions for life in planetary systems. Finally, an NRAO might be stepping into search for aliens, and then finally, when we're shown in the media about aliens, it would actually be something that we do. Can also look at galaxy evolution. So again, this is something of looking at, it's known as flux density. The point of this plot is just simulating, look, we're going to be able to see way more, way cooler stuff. Look, ALMA and the VLA doesn't get down low enough to be able to see this stuff, and the ngVLA will. Give us money. But of understanding formation and evolution of galaxies. Don't have a fun image for this, but we'll be able to look at pulsars to be able to test the fundamental gravity in the universe. This is something that is highly debated and contested, and we'll be able to observe pulsars to high resolution to be able to observe it. And also look more at supermassive black holes and the evolution of those and how they move and what they're made of, and we still don't understand how they formed, so maybe we can learn about that as well. And be able to observe a lot more than what we've been able to up to this point. So there's a lot of really cool science that we're going to be able to do, a lot of fields of astronomy that have been untapped so far with the VLA. But then we get into actually my job, which is testing the VLA, the ngVLA. Because we built a prototype antenna, and we need to make sure it works before you build 218 of them. So some of the testing that I will be doing is looking at pointing and focus, RFI, interferometer, using the VLA with the ngVLA prototype as an interferometer, and then all of that again with precision. So I'm going to talk about each of these things now. I'm not expecting you to understand just by me putting them as a point. So, pointing and focus. You have your antenna, you want to point it at a source in the sky. So you point your antennas there, you look at it. Now you've told it to look here, and then you look at your data, and actually it was looking there. It's not great, so we have to actually test to understand the difference in where it was pointing versus where we told it to point. So we have to make pointing models. Sometimes this can be an issue with hardware. That's great if you have a prototype where you can change the hardware before you build 218 more antennas. So you need to actually test, is it pointing where I told it to? Is it in focus? Can you actually see what you're trying to see? Again, these are things that we need to test because sometimes the design of your telescope means it's not in focus. Some of you are familiar with the Hubble Space Telescope needing to essentially get glasses because it was out of focus. That can happen with radio telescopes. So we need to be testing to see, is our antenna actually able to point where we tell it to point and be in focus. Another thing is RFI monitoring. So as I said, there's a lot of other things transmitting. So this is an example of a plot. All of those spikes are RFI. That's not the sky. That's other things. That's cell phones. That's satellites. That's TV stations. We need to be aware of the RFI environment and what your antenna is seeing. And more importantly, is your antenna contributing to the RFI environment? Basically, is your telescope screaming so much that the antennas around it can hear it? Because that's not good. So I actually did preliminary work with our prototype antenna to ensure that turning the antenna on and having the motors on wasn't causing a problem for the VLA. So I did testing of various states of the antenna being on, and saw that while some things were changing around, there was no significant difference for any of our tests. And this is another way of looking at it, where you can see basically nothing in each of those boxes is during our test of turning the antenna on and off, and there's no difference in that entire time. Nothing changed as you're going down in time between turning it on and turning it off. So that's really good. And now as we install more electronics, we're going to have to keep doing that to be ensuring that our electronics are not interfering with the rest of the telescope. Another thing is holography. So holography is very similar to holograms. Basically what we're able to do is you find a bright source and you just scan back and forth constantly with your antenna, not stopping, not looking at a calibrator, just moving up and down, back and forth. And what that does is it creates an image of your antenna, the surface of your antenna. So this is a program that's still being worked on to be able to perform holography with the VLA. So we have this image of a test done with the VLA where you can see there's these 3 panels on the antenna that are not where they're supposed to be. This bright yellow is saying, hey, this panel is higher than everything around it, and this dark section is saying this panel is lower. So that's not good, because that's going to affect your light reflecting into your receiver, because it's not going to be reflecting off of these panels the same way as it is the rest of your antenna. So this program, when you do this observation, you can then look at the surface and then actually have it calculate how much the screws on the panel need to be adjusted to get the panel back being flat with the rest of the antenna. So this is something that's very important for the health of our antennas. Things move, especially if your antenna is moving all the time. Things can adjust, things weather. And so this right now is hard-coded for the VLA. The ngVLA is not going to be round like this. It's actually sort of rectangular. So the program is hard-coded to produce everything with the antenna being round. So we need to make adjustments to be able to actually look at the surface of the ngVLA to be able to get similar plots and similar information to ensure that it is all flat and the way that it's supposed to be. But additionally, because the design is different, the secondary reflector is in a different location as well, that affects how we actually read this holography information. So that's another thing that I'm going to be working on, is just looking at the surface of the antenna. So this is our prototype antenna. This is it on site. It was manufactured by a German company, MTEX. They came on site and constructed it, so you can see instead of being round, it's sort of rectangular. Instead of having a central secondary reflector up top, it's lower and connected by these struts. It's much smaller. You can actually see people standing in comparison to the antenna. It's not nearly as big and high up as the VLA. So this is very cool. I've been able to look at it from a distance. So the plan, we have this antenna constructed. So the plan was they were going to turn the antenna over to us in April, May of 2025. I start in July of 2025. So I jump in to the testing of this antenna. I get thrown in, they've already started testing. I'm learning on the job how this all works. And then in April of 2025, there was a windstorm of upwards of 70-mile-an-hour winds, and the secondary reflector was not fully installed yet, and it broke off of the antenna. So that video that I showed of the antenna moving was taken in December when MTechs had come back to site to finish building the antenna after they had to go back to Germany and redesign and remanufacture all of the parts to give us a secondary reflector again that won't break when it encounters winds. We don't get 70-mile-an-hour winds very often, but it does happen. It's windy there, so it's not good. So now testing is going to begin in February of 2026. There have been delays beyond this, things pushed back. So I started in July. We haven't started testing the antenna I was hired to test yet. So again, this video that I love is from December, because it was the first time we were allowed to send any signal to our antenna. MTechs gave us the okay. We were allowed to tell it to move. So we got to test, can we tell it to move, and will it move? And it did. And that's the only time we've gotten to interact with our antenna. But we're almost there. There was a meeting today about updates on whether next week we can start testing, and I know the answer was no. But we're so close. I can almost do the job I was hired to do. So thankfully I wasn't having to very quickly train on the job of how to do all of this stuff. But I'd like to do the job I was hired to do. So I'm very excited to get to start testing my brand new antenna. So also that is not the actual secondary reflector. That is a stand-in. So also the speed at which it moves up and down is actually slower than how it's actually going to move, because this is not balanced correctly. So it's actually going to be able to move up and down faster than it is right now. So it'll move even faster. So it's very exciting and fun stuff for me. So, a summary. Radio astronomy is cool. I really like it. There's lots of stuff that you can do. VLA and VLBA have been producing outstanding science, furthering our understanding of the universe. The ngVLA is going to be 10 times as sensitive, so even more work is going to be done in understanding our universe and new fields that we're going to be able to do. And it's also going to make really cool images, because with all of those baselines, it means you can make images. The prototype antenna is currently under construction instead of done being constructed, but we're almost there. And it has to be thoroughly tested before the full array is built. And before I let you go for questions, some advice from an alumni. I don't know how many of you are actually physics majors, but for those of you who are, take linear algebra before you take quantum or math methods. I made the mistake of taking linear the same semester as quantum. Shout out to Dr. Hall for passing me, because I was suffering taking them at the same time. Math methods I took later. It was the easiest upper division physics class I've ever taken, because I had taken linear algebra already. So do that. Appreciate the cost of parking while you have it. I did my PhD at ASU. You have to buy a parking permit for a single parking lot. It is not applicable the rest of the area. There are 3 parking lots that are close to 90% of campus. Each of those parking lots for the year, it costs $780 to get a parking permit. And because they are near everything, they are sold out immediately. So to pay for parking for the day is $16. I did not appreciate the cost of Fresno State parking while I had it. Please appreciate the parking cost. Maintain hobbies outside of school and work. You need them. Life is hard. The world is the world. You need to have things to think about that isn't school and work, because also I've talked to people whose entire personality is physics, and they are very boring people to talk to. It's really nice being able to talk about other things. So it helps your mental health and also helps you interact with people. And then just email people. I've gotten emails from people about like, hey, I read the work that you did and thought it was really interesting. Can you tell me more about this? And that's great. It feels great. Sometimes you won't hear back because academics are very busy and they have hundreds of emails in their inboxes, but sometimes you hear from someone who's very excited to hear that someone's interested in their work, and it can be really cool and make connections, and then you do research with them. So just email people. And my email is up at the top in the corner, so you can email me if you're interested. But I'll leave the summary slide up as a reminder of everything that I talked about, and I will open it to questions if anyone has them. Thank you.
Do the antennas have active control to retain their shape?
No, there is all of the structure behind it, and then we can do maintenance to adjust everything as it ages if things need adjustment, but there's no like electronic controls that are keeping it. Yeah.
You said that in the current iteration that calculation for the calibration of each like module is hard-coded. Do you know if the plan for the next generation is to hard code the new one or make like a system that you can input the geometry?
Basically what a lot of things with the software that we use at NRAO is you get an updated file that gives you all of the information about your telescope, and then that gets substituted in. So like in this case, we could substitute in saying, hey, this is the information about the size and shape of everything for the ngVLA, use that instead of the VLA. So I think that's probably so it'll be modular instead of it's in the code itself. So it can accept like which telescope antenna you're looking at.
I just like to understand the anatomy of the radio telescope. You kept referring to the secondary reflector. But isn't that actually the receiver?
It
There's no actual
depends.
secondary reflection, is there?
It depends on the antenna. So the in some cases, so the VLA actually does have receivers on the secondary reflector, but most of the receivers are in the center of the dish. So it's reflecting off and then coming down and being recorded by the actual receivers and feed horns. And for the ngVLA, I believe it's something similar where the receivers are actually going to be separate from, there's going to be some equipment actually on the secondary reflector, but then it is still actually going to be reflecting into receivers. And part of why that is done for like with the VLA is actually that secondary reflector will move. So it'll actually point at what receiver you're trying to observe in because they're each separate. So it'll actually move to be able to point the light into the receiver that you're trying to use.
And the receivers, there's different sensitivities for different wavelengths?
Yeah.
Oh, thank you.
Because the receivers have to be different sizes depending on
So
what
it really
wavelength
does-
you're
It
trying
really
to.
does redirect something?
Yes.
Oh, thank you.
I saw that.
Yeah, you finally got to move the antenna after the extra repairs. Were you able to tell whether it did what you wanted it to?
It did for the most part. There was some, so I'm not involved with all of the hardware testing of the antenna. I wasn't involved with that, but there were some hiccups with the electronics and the signal actually receiving and timing issues. I learned about negative time, hated that. But a difference in timing of your receivers versus actual time versus I don't even know what. So there were some hiccups there, but for the most part, it did actually do what we told it to do, and we were able to take that data from that test to be able to apply for the future of making adjustments to things and fixing things on our end.
Are there any specific wavelengths that you guys are hoping to probe to kind of understand? Is there like something specific you guys are looking at?
I don't know, because I don't work on that. I don't look at the sky, I look at the telescope. So I actually know that range of frequencies. I have no idea what those different frequencies are used for. So I don't know.
When is it planned to be operational?
So we are expecting to still be testing it through the rest of the year, and At parts of that time, we will actually be doing observations in connection with the VLA. But I think it would be next year that it would be technically operational, but it is still just a prototype. So it's just the single antenna, so there's not a whole lot different that we would be seeing with observations with it versus without it. Construction on all of the other antennas will start in a couple of years. And it'll be, we're building 218 of them. It's gonna be a while. The goal is within 10 years is having it fully replace the VLA and VLBA, but especially, you know, with delays like this, it's sort of up in the air.
You mentioned use of the VLA with the ngVLA. So I gather when the ngVLA is operational, the VLA will continue.
For a time, they'll be operating when we're constructing, and so like we'll be building the core, which is at the VLA site, and so those will be slowly coming online as we're building. But eventually the plan is that when the ngVLA is fully operational, the VLA will be decommissioned. So in potentially 10 years, the VLA will no longer be in operation, but that's still being debated. And also a lot of it comes down to funding, of can we be operating these two massive telescopes at the same time. So it's still uncertain, but there will at least be a period of time where both of the telescopes will be observing simultaneously.
Are there any other precautions you guys are gonna take? Because you mentioned that there were like 70-mile-per-hour winds and it knocked off. Like, is there something that you guys are gonna do in the future to maybe like keep it safe, make sure it doesn't break again?
So as they've been constructing it, reconstructing it, they've been fully tightening all of the screws as they go along. You know, instead of leaving them loose as you're still putting everything else on, they've been basically getting it as solidly attached as possible before stopping for the day. And they also just improved the strength. So now some of the struts, actually in stress testing, the failure point were the bolts that were used and not the actual like struts and equipment. It's the massive bolts that are being used to attach these things that would fail first. So basically they re-engineered things to try and ensure that nothing's moving anymore. But also now the time of year, we're not getting as high of windstorms, so it actually also hasn't been a concern, so.
So is there any collaboration between ngVLA or VLA and LIGO, for example? Like
Yes,
neutron? Okay.
actually, I didn't mention that, but there has already been work. I believe it was the VLBA actually responded and observed gravitational waves. They were able to observe it happen. And so ngVLA is going to be able to continue that as well, of being able to, you know, when LIGO gets a trigger, we'll observe, we'll point at where it is and observe. And like I said, I believe it was VLBA already actually successfully did that, of being able to observe the neutron star merger that produced those gravitational waves. So yeah, there is collaboration there.
I have a question. Is it, I think the range is quite high. You've got microwaves nowadays. I mean, you're going gigahertz. You're no longer quite in the.
Yeah, we're going to be pushing what is visible from the ground, but it is still, like I had said originally, radio astronomy is defined as being up to 900 gigahertz. So 116 is still within that, but I think we are going to be, you know, we're pushing it for ground-based, but there's still more that can be done there.
Like you mentioned chemistry, like what molecules can be in that range?
No idea.
Usually it's used for infrared, the infrared, we see that.
No idea, not my
Probably
specialty.
indirect, maybe. Any questions? If not, let's thank again our speakers.